Before you start watching this video, please make sure that you've seen the previous video that I did, which dealt with critical numbers, and that you've also covered off the stuff that we did when we were in the school on increasing and decreasing parts of the function. It's critical that you understand those before you watch this video or deal with this video. We're going to be looking at rational functions and the kinds of asymptotes that come with those rational functions and how they can affect what the graph looks like. But we're still talking about the critical numbers. We're still talking about where it's increasing and decreasing, the maxes and the mins, all that stuff that was dealt with from before. So definitions, vertical asymptotes. Vertical asymptotes, as you know, those exist at x values that make the denominator equal to 0. And that means that factoring it is useful because then that's much easier for you to see where those vertical asymptotes are. Horizontal asymptotes, those will exist when the degree of the numerator is equal to or less than the degree of the denominator. If they're equal, it's just a matter of getting the ratio of the lead coefficients. If the numerator is less than the denominator, then it's simply just the x-axis, the y equals 0 line. Oblique asymptotes occur when the degree of the numerator is 1 greater than the degree of the denominator. Now, you can have differences between the degrees of more than 1. You could have a difference of 2. You could have a cubic over a linear. That's a difference of 2. And what would happen is that you have basically a quadratic asymptote. But we're going to restrict our discussion to only looking at oblique asymptotes. Critical numbers were discussed in the previous video, and we know that that's when the derivative is equal to 0 or the derivative does not exist. Whatever values of x that make that happen, those are what we call critical numbers. We're going to have first derivative tables just like we had in the previous video, but we're going to also have to take into account these restrictions in the domain as well. First question is this. Looks like it's a case of a higher degree in the numerator than the denominator, which is when we say we might have an oblique asymptote. But we should try to factor it first before we jump to that conclusion. See if there's anything about this which might make it a simpler rational function than it seems at first. If I did that, I would end up with right away two common factors of the numerator and denominator of x squared. Those will cancel out. I can factor it further. Turns out that these will also cancel out. So what am I left with? I'm left with a linear function. Didn't seem that way at the beginning, but that's exactly what we're dealing with. And if it is a linear function, it's a linear function that has what we call holes in it. No asymptotes, but holes. And how do I get where those holes are? Look at the things that we eliminated, the x squared. What would have made this x squared would have been a 0. What would have made this x minus 1 would have been 1. So that's where those holes are. Those are values of x that are actually restricted, right? In the original function, those are restricted values. 0 and 1 would have been restricted values. In the reduced form, no, there was another problem. And we can actually use a reduced form to find out what the coordinates of that hole are. So the 0, which is what we said we got from this x squared that was canceled out, put that back into this reduced form, we get 0 minus 2. Put the 1 that we said was restricted into this, we get minus 1. So these are both of the holes that exist in what is essentially a straight line. So here's my graph. This graph is just a line. And you can see it has these two little circular holes in them, one at the 1 minus 1 and one at the 0 minus 2. And I've labeled them both for you to be able to clearly see them. So no asymptotes, just holes. This one is a case where we have a degree on the top and on the bottom where they're both the same. And if you took the ratio of the lead coefficients, both threes, I'd have that the horizontal asymptote is y is equal to 1. Okay, we should have factored it. So we're going to factor it now. So when we factor this, we end up with something which cannot be reduced. So we can't reduce it, but it does help us to see where the vertical asymptotes are. So these two denominators here, the two factors in the denominator, tell us that we have vertical asymptote at x equals minus 1 and x equals minus 1 over 3. Great. Y-intercept, that's easy. That's just setting your x 0. We did that from grade 9. And in this case, if I put 0 for my y, so here's my, sorry, for my x, sorry. If I put 0 for my x, the top becomes 0, the whole fraction becomes 0, the whole rational function becomes 0. So 0, 0, the origin, is going to be my y-intercept. Similarly, if I set my y to 0, so put 0 on this side of the equation here, that means if I cross multiply, I'm going to get 3x squared equals 0, which means that the x is going to be 0 as well. So my other intercept at x is also the origin. So the origin is the x-intercept and the y-intercept. Great. All right. Now I'm going to take the derivative. And we're going to need the derivative to get the critical numbers. So I've done that. And I'm not going to go through every single step of derivatives because we've been through this before. But yeah, I have the derivative of the top multiplied the underived bottom. Gives me all of this stuff here. And then I can, get my like terms. And at the end of the day, I'm going to end up with this. And it's good for me to be able to factor this numerator because in this form, it makes me see that, again, I'm trying to find where the function is increasing and decreasing. One of the things that we talked about in one of our previous classes was where is the function increasing or decreasing. The bottom of this function is always positive, so I really need to focus on the top. And it's always positive, by the way, because I'm squaring it. The top gives us this. This has two, it's a quadratic, it has 2 zeros. So if I were to draw that quadratic, just imagine a quadratic here with 2 zeros at 0 and minus a half. Then the function would be increasing between minus infinity and minus a half, and then from 0 to infinity. That's the part that's above the x-axis. And it would also be decreasing between minus a half and 0. If you think about what this quadratic looks like on a graph, what part is above, what part is below, that should be hopefully fairly obvious. How about critical numbers? Critical numbers, again, come from the derivative. So what is making this derivative 0? Again, focus on the top. Critical numbers would be at 0 and minus 0.5. Those are your critical numbers. Your critical points, again, put those critical numbers back into the original function to get the critical points. It turns out to be 0, 0, and minus 0.5, minus 3. Okay, so I'm going to set up a table now. And in this table, what I'm going to have is my entire domain going from minus infinity to minus 0.5, minus 0.5 to 0, and 0 to infinity. Those come from my critical numbers. I've broken it up like I did with the previous video. And now I'm going to just pick a number in each interval. I'm going to pick minus 1, minus 0.25, and 1. And I'm going to put the factors along the side because for me to evaluate where this derivative is positive or negative, is really the top I'm going to be focusing on because the bottom is always positive. I've said that before. The top will determine whether the whole derivative is positive or negative. So let's do it a little piece at a time. The 6x and the 2x plus 1 on the side here. Putting the minus 1 into the 6x gives us a negative. Putting the minus 1 in 2x plus 1 also gives us negative. Count my number of negatives. Again, I'm repeating stuff that was in the previous video. If it's an even number as it is, then this whole thing becomes positive. Put minus 0.25 into the 6x. Put the minus 0.25 into 2x plus 1. Again, this turns out to be negative and positive. So that's a one odd number of negatives. So this is going to be negative. If I put 1 into each of these, I'm going to end up with all positive. So this part's positive. What is this telling me? This is a max here because I'm going from being a positive to a negative. So that's the max. This is a min here. That's a lot of information for us to be able to draw this graph. So let's see if we can come up with a graph. I've repeated some of the information here that we had from the previous slide. And what I'm going to do, and there's my min and my max. I didn't actually, well, I'm going to show you the graph now. So here's the graph without the actual graph itself. Here's a grid without the actual graph. So I put in the asymptotes, one here, one here. These are both the vertical asymptotes. That's the horizontal asymptote, which we talked about from the previous slide. This 0, 0 is both the intercept and it's also the minimum value. This minus 0.5 minus 3 is my maximum value. And again, it's a local maximum, but it is a maximum. And can we see what this might look like? We know the function is increasing and decreasing at various points. I'm thinking if there's an asymptote here, and this is a minimum point, I'm probably going to come down to that minimum, then start going back up towards asymptote on this side. I'm probably going to come up to this maximum and start coming down. And then over here, I'm thinking since there are no other x or y intercepts, the only way that this part can look is if I were coming along and sort of trailing beside both of these asymptotes here. Well, that's what I'm going to do. I'm going to put the first one that looks like this here and another part over here. And then down here, I'm going to put a part that comes up. Now, I know my lines are very crude and I'm doing the best I can. And so I'm going to show you a Desmos version of the same thing. That's a much better picture, but it's exactly the same idea with a minimum here and a maximum here, and it's still following all the asymptotes that we talked about. So sometimes just having those clues, but here's the other thing that we need to look at. I'm going to go back to the previous slide for a minute. Is the function increasing between minus infinity and minus a half? Minus infinity and minus a half. Well, it is broken apart by the asymptote, this vertical asymptote, but it is increasing here, and it is increasing when I go from the asymptote up to that minus a half. So that's still true, even though the asymptote breaks apart the things that are increasing. Is it increasing after the 0 to infinity? Absolutely is. It's increasing over there. Is it decreasing from minus infinity, from minus a half to 0? It is decreasing from minus a half. It is again broken up from this little part right here, but it is decreasing anywhere from minus a half up to 0, even though there's a part that interferes with that in the middle here. So all of that squares with what we said before. Let's go back and look at problem B now. In problem B, we're going to deal with a numerator which is a higher degree than the denominator. So how is that going to work? Well, we should be factoring it to see if this can break down to something simpler. But, well, let's go ahead and factor it. So let's factor it first. So we factored it. And then secondly, I'm going to see if I can come up with where this oblique asymptote is. We expect an oblique asymptote because the degree of the top is higher than the degree of the bottom. So what I did is I set up remember the synthetic division table on the side here. The 2, the minus 7, and the 3 are on top. The minus 5 is on the side. I bring down the 2, and you should remember this from advanced functions. And eventually I end up with a 2 and a 3 and an 18. These two give me the oblique asymptote because I'm going to be able to write the function like this: the 2x plus 3 plus the remainder over the divisor. This is the quotient. The quotient is actually the oblique asymptote. So the 2x plus 3 is actually the oblique asymptote. And there it is right there. Okay, what about if we had to get a vertical asymptote? It's whatever makes the denominator 0. So in this case, it's just simply x equals 5 because the denominator here is x minus 5. So x equals 5 would make that equal to 0. My y-intercept already got the oblique asymptote. We already have the vertical asymptote. Let's get the y-intercept. Set x to 0. Setting x to 0 up here in the original function gives me minus 3 over 5 as my y-intercept. My x-intercept, set y to 0. Well, that just comes from whatever this numerator would give me. And this numerator gives me 3.5 as both of the x values that make the top become 0. So I'm going to take the function now, the original function, and I'm going to find the derivative. Again, I'm not going to go through the entire step of finding derivative. You are experts at that now. Just trust me on this one, that derivative is what you just saw me put on the screen. And that is factorable, which is useful because if I factor that, I'm going to end up with, by setting that denominator to setting the derivative to 0, I'm going to end up with critical numbers at 2 and 8. And you can follow that through by factoring it yourself. And my critical points are 2, 1, and 825. So again, once I get my critical numbers, I can put those back into the original to get my critical points. Fine. How can I graph this? I have the 825, which is one of the critical points. I have my 2, 1, my other critical point. I have my x-intercepts. I have my y-intercept. I have my asymptotes. It's kind of obvious what that's going to look like. I'm going to follow this along here. So this is probably this critical point is probably a maximum. This other critical point is probably a minimum. And here's my rendition of that. Both of them, again, not the greatest drawings, but again, what I've done is I put together a Desmos version of it, but it does still follow all the things that I said it should follow. If I went back and looked at my previous slide, then all the things that we talked about are there. Here's a Desmos version of it looking a lot better than mine. There is success criteria, and hopefully that all made sense.